Just too small amount. First of all, who didn't take these papers? Everyone took these papers. The papers of reimbursement. Okay, great. The second question. In case you leave tomorrow or on Friday, don't forget that you should, especially the students, should check out of their hotel before 9 a.m. So please bring your bags here to the conference, okay? The rooms must be clean and clear before 9 a.m. Well, thank you very much. Now, let me present you Hugo Parlier, who will speak about combinatorial aspects of Teichmüller spaces. Thank you.
Thank you very much for the introduction. Okay, so I was sort of midway through my introduction when I finished last time. So I was going through examples of combinatorial moduli spaces, and I was talking about the curve complex. And in particular, I was talking about the one skeleton of this complex, which is the curve graph, and vertices of this graph are isotypic classes of simple closed curves. So let me just keep on going with an example here. So I can take different simple closed curves on this. So here's a simple closed curve alpha. Here's a simple closed curve beta. Okay, here's maybe epsilon. Let's see what else. Here's a simple closed curve gamma. Yes, green, and then here's one, maybe delta. Okay, and so I want to look at what this looks like, what these represent in the actual curve complex. So I have alpha, and it is disjoint from gamma. Okay, so I can alpha and gamma span an edge. But it is disjoint from beta. Okay, so alpha and beta span an edge. It is also disjoint from epsilon. So they span an edge. Okay, epsilon is disjoint from beta, for instance. Okay, so they actually form a triangle, these three. What else do I have here? Epsilon is not disjoint from gamma, so they don't span an edge. I'm missing here, epsilon and delta, they also span an edge, and gamma and delta span an edge, and so on and so forth. Okay, so this is just giving you a very small picture of a bunch of curves on this particular surface. Okay, so in terms of the actual complex, because these three can be realized disjointly, they also span a triangle. Okay, but in terms of the graph, we're just looking at the one skeleton. Okay. So let me just make a small observation, and that is that this graph here is connected. So I'm going to denote both of these things C of gamma, okay, and hopefully it'll be clear what I'm talking about. In general, it'll just be the graph. So it is connected. Okay, so why is this true? And it's maybe not very difficult to see why this is true. Basically, this is true because if I have any two curves that lie on this surface, on any given surface, then I can find another curve, okay, that is disjoint from one curve, okay, and it has less intersection number than the other curve that I already have. So let me make this more precise. So just the idea of why this is true. So if I take one curve here, suppose I have some curve alpha here, and then I have some other curve beta. Well, if this other curve beta is disjoint from alpha, then they span an edge and they're connected. Okay. So I have to suppose that I have some other curve beta, and I don't exactly know what it looks like. Okay, it's some very complicated something. This is my curve. Okay, and it's not clear at all, if you have a very complicated curve, how you get from alpha to beta in this curve complex. Okay, so one way of thinking about this is I'm going to cut along alpha. So I have one copy of alpha here. I have another copy of alpha here. And then I have some complicated surface here. And now what beta looks like on this is going to be a collection of arcs. Okay. Okay. Doing all sorts of things. Okay, so this is what beta looks like. Okay. If there happens to be a curve that lies on the complement of alpha and beta, then I can obviously go from alpha to this other curve, and then to beta. Okay, so that's easy. So I have to consider the case where I can't do that. Okay. So what am I going to do? Well, the way I've done this, I've unpasted this, okay? And at one point there has to be some point here that's glued to some point here. Okay, the way I've done it. So what I'm going to do is I'm going to choose one particular arc of beta, maybe, I don't know, this one. I'm going to choose it. I'm choosing just this arc. Okay, and I'm going to find a curve using that arc. So what curve am I going to find? Well, I'm going to find a curve. So this arc here, if I just look at this arc, and I forget about the rest. Okay, this arc here looks like this. Okay. This point here that it's attached to is going to be some point over here. Okay, so here are two curves that I can create using this arc. I can create the curve that does this, okay, and then that goes here and goes through this point. Maybe nobody can see that. So here's an isotropic class of curve that goes like this. Okay, that's one possible isotropic class of curve. Here's another possible isotropic class. I can do this. Okay, and I can go around and come up here. So I'm going to go like this. So what I claim is one of these two curves, okay, because it goes around here and then it starts going through all of alpha. One goes to alpha and goes to the right. The other one hits alpha and goes to the left. Okay. One of these two curves doesn't intersect beta that much. Okay, more precisely, one of these two curves has about half the number of intersections between alpha and beta. Then I'm going to replace alpha by this curve here. Does that make sense? So this curve here, I'm going to choose one. this alpha tilde, the intersection number between alpha tilde and beta, is going to be less or equal to the intersection number between alpha and beta divided by 2. Okay? Because along this path it doesn't intersect beta at all, and then the only intersections I get with beta is when I go around here, when I go around here, possibly. Maybe much less, okay? But I'm just finding this. And this curve alpha tilde also has the property that its intersection number with alpha is actually equal to 1. Okay, that's exactly how I've constructed it. So alpha tilde and alpha, they don't span an edge in the curve complex, but they're very close. Okay, so alpha tilde and alpha, they intersect once. So this actually means that their distance between alpha and alpha tilde in the curve graph is actually equal to 2. Okay, so I can move. So why is that? Well, because this is my alpha. I come back to the original thing. This is my alpha tilde. Okay, and then I can choose another curve that's here, that's disjoint from alpha and alpha tilde. Okay, so now their distance is actually equal to 2. So by moving 2, I can reduce the intersection number by a half. That's what I'm doing. Okay, and if I can reduce the intersection number by half, I can keep on doing this until eventually I get to 0.
How do you know that curve is essential?
This one here?
Yeah. No, the new one that you drew.
So this is alpha tilde. Yeah, this one here?
Like, how do you know that it will be a point in your curve? Because that could be a torus with a cusp point, right? And when you draw alpha and
This one here?
you find a new curve. Yeah.
Here? Yeah,
That's
okay,
this
so
one.
you're hitting on exactly what I'm
Okay.
going to. Okay, so all of this works, except for if this one is a puncture.
Okay.
And I've also not said all the possible cases. This is just sort of one surgery case where you can actually find something. Okay, so there's a bunch of problems that I haven't sort of hit on. Okay, but you can do this type of argument to hit all possible cases. And the one possible case which I absolutely cannot do with this argument is the case of a once punctured torus, or some other cases. For instance, if I just had a torus, I can't do this argument. Or if I have a 4 punctured sphere, or if I have a 3 punctured sphere, etc., etc. So there are some special cases. Okay, one of them is when sigma belongs to one of the following sets. Okay, so one possibility is that sigma is just a torus. Okay, one possibility is sigma is a torus with a puncture. Okay, and the other possibility is that sigma is a 4 punctured sphere. And of course, there's another possibility which is even more special is when sigma is just a 3 punctured sphere, in which case there are no isotopic classes of essential. So the curve complex is empty. But okay, so I won't talk about that. And in these cases, the problem is that any two curves, two essential simple closed curves, intersect. So what are the so we have to define something else for these particular cases. Okay, so let's look at what happens for the curve complex of this. So what is the appropriate notion? Well, I've defined intersection, two things that being spanning an edge. If their intersection is equal to 0, I can replace that with their intersection being minimal. Okay, so for these cases, alpha and beta, if the intersection between alpha and beta is minimal. Okay, and what is minimal? Well, in the case of a torus or a once punctured torus, this is equal to 1. Okay, and this is equal to 2 if sigma is equal to this. Okay. So in this particular case, we get interesting curve graphs. And what do they look like? So they're all the same curve graph, actually, for these 4 cases, in these special cases. And what does the curve graph look like here? Okay, so I'm going to do it for a torus, and then you can do sort of exactly the same for the films. So one way of thinking of a torus is by thinking, of course, of a square, which I've associated. Okay, and I can look at isotopy classes on a square. And what does this correspond to? Well, there's different ways of saying this. One way is saying that isotopy classes on this correspond to unoriented homology, primitive homology classes on the torus. Okay, but more simpler, I mean, if I just look at this is a square torus, and I leave from a point, and I start going around, okay, this orbit is only going to be periodic if the slope is rational. Okay, so what I'm going to get in the end is isotopy classes are in one-to-one correspondence with rational slopes. Okay, and I want my rational slopes. I do want to have an exceptional case. So for instance, this guy here, okay, this guy corresponds to slope 0. And this guy here, okay, this corresponds to slope infinite. Okay? And the way I'm thinking of infinite is 1 divided by 0, and 0 here is 0 divided by 1. So what I have is actually one-to-one correspondence with things of the form p divided by q. Okay. So, I mean, in fact, to be precise, this is actually oriented, but I mean, it doesn't. Okay. And then, what is the intersection number in this case? What does this correspond to? So, if I have 2 slopes, 2 rational slopes, how do I compute how many times the actual corresponding geodesics intersect? Well, there's different ways of seeing this, but essentially a simple calculation tells you that the intersection between a curve corresponding to PQ and a curve corresponding to RS is going to be exactly PS minus QR. Okay, an absolute value. Okay, so what this means is that I'm joining 2 rationals. Okay, so my vertices, in this case, of this. So vertices are the rationals union infinity. Okay, and PQ is joined to RS if PS minus QR is equal to 1. And this is a well-known graph. This is called the fairy graph. Okay, what does this fairy graph look like? There's different ways of visualizing it. But the nicest, well, one of the nicest one is using the hyperbolic plane. And this will be 0, this will be 1. No, that's not true. That will be infinity. This will be 1, this will be minus 1. Okay, so it's easy to see that 0 and 1 are connected. Okay, what color should I use? Red. It's easy to see that infinity and 1 are connected, and it looks like this. Okay. And then you can just keep on going, and this is what the graph looks like. Then I just keep on going. Okay. So this is the curve. Okay. I'm going to come back to this graph later. Here with this. So just an observation, although I've never said this explicitly, it should be clear from the type of thing I'm saying that the curve graph is an infinite graph. So as opposed to the other examples I gave. And, well, this is a special case of this infinite graph. And so you have a question about what you might want to, what this graph looks like in general. And it's not too difficult to see that this graph here is, if you analyze it correctly, it's quasi-isometric to, well, okay, I'm not going to, it is, but that's not what I want to say. I mean, it's hyperbolic. It's Gromov hyperbolic. This is an object. Okay, it gives you a Gromov hyperbolic infinite graph. And this is true in general. This is sort of an important theorem of Mazur and Minsky. Okay, that this graph here, which is quasi-isometric to the complex, is Gromov hyperbolic. Okay, I'm not going to explicitly use this in any way. I'm just using this as context. But if you want to look at the rough geometry of this curve graph, then it always gives you something that's hyperbolic, and you know, which is interesting for many reasons. So the goal, now that I've finished sort of this introductory part, the goal is to show how you can get from Teichmüller space to another simplicial complex that's related to this, and then to study this simplicial complex in more detail. So, part one. From Teichmüller spaces, to the Pants graph. Okay. So let me just remind you a little bit of what Teichmüller space is and how this relates to all of that, and just to fix some notation. So I'm going to divide this board into two parts. And here's going to be Teichmüller space associated with sigma. This is so the way I'm thinking of Teichmüller space is the space of marked complete finite area hyperbolic structures on this topological surface again. Okay, and one way of thinking of this so in this case I have something that's genus 2 with punctures. I'm going to put a complete finite area hyperbolic surface on this. So what this means is that in the marked points, okay, so on gamma I should say more precisely minus the marked points. Okay, because I want something that's complete in finite area. In the marked points I'm getting cusps. Okay, so this is sort of what a hyperbolic surface looks like. And one way of thinking of that is I can look at a Pants decomposition of this. I can break it down into a pair of Pants. Like such. And now what happens is, if I have a hyperbolic metric on this, I have a bunch of isotopy classes that break the surface down into pairs of Pants. Okay, so for those, pair of Pants is topologically a three-hole sphere. Okay, so it's a maximum, in terms of the curve graph, this is a maximum simplex. Okay, in the curve graph, a maximum set of disjoint isotopy classes of simple closed curves. Because this metric is hyperbolic, then in each one of these isotopy classes, the metric looks everywhere sort of like this. Okay, so in each one of the isotopic classes, there's a unique geodesic. Okay, so I take this unique geodesic, these are these red curves, in each one of the isotopic classes, and this tells me what happens on, I have a bunch of pair of pants when I cut along this. And this tells me exactly the lengths of the three boundaries of the pair of pants. So what happens for hyperbolic surfaces is that if you know the three lengths, then you know the hyperbolic structure on this pair of pants. Okay, it's a sort of an elementary exercise in hyperbolic geometry, which I won't go into because I don't really want to talk too much about that, but to show that these lengths here determine the geometry of this pair of pants. And so what's left to determine the whole surface, if you know exactly what's happening on the pairs of pants, is you have to know how they're joined together. And this is recorded by a so-called twist parameter. So if I have a pair of pants here, and another pair of pants here, I want to record how I'm joining them together. Okay, I have to know how I'm going to join this one to this one. And so I have to have some form of way of computing this. And what I do is I look at orthogonal curves like this, for instance. And I look at how far away they are apart. And I record this distance. Okay, and this distance here is the twist parameter. Okay, so in all I have the lengths of these curves. I have the way that they're glued together. And these give me Fenchel-Nielsen coordinates. And okay, so without going into the details, what I'm doing here is this twist parameter, I'm actually letting it belong to the reals. So I'm not only looking at the distance of how these perpendiculars go, but I'm also recording whether or not I've twisted several times. So I have some idea of what twisting zero means. I fixed that. That means a zero twist, when that thing is exactly when that thing is. And then I'm going to differentiate between this surface and the one that I twisted around once. Okay, so from an isometric point of view, this doesn't change the surface. But it does change the surface from a Teichmüller space point of view, because this is a space of marked complete finite area. So there's a topological marking that comes into play here. Okay, so Thurston gives the example of, if you think these two surfaces are not the same, then take a little child, take a pair of pants, twist the pair of pants 7 times, and now try putting the pair of pants on the child. Okay, and now tell me that it's the same surface. Okay, so it's not. I'm just somewhat artificial. And the point is that what I can do here is these length parameters. So I have 3g minus 3 plus n length parameters. Okay, and these belong to the positive reals, strictly positive reals. And 3g minus 3 plus n twist parameters. Okay, and these belong to R. Okay, so this set of parameters is the Fenchel-Nielsen coordinates. And you can also take this as a definition of Teichmüller space if you don't want to worry about anything else. Okay. Okay, and then this space here is a topological space given by this topology, for instance, or a deformation topology, deforming one hyperbolic surface into another. But it also has a number of metrics. And I think, if my information is correct, that you guys have already seen the Teichmüller metric on this. Okay, so what is the pants graph now? This is a graph. And vertices are exactly the pants decompositions of the topological surface. Okay, so these are sets of isotypic classes of curves. Gamma 1 to gamma 3g minus 2 plus n disjoint essential simple closed curves. Okay, and how do I join two Pants decompositions? Well, for one thing, how do I get another Pants decomposition from a first Pants decomposition? So one thing I can do is I can change an element of the Pants decomposition, like this one. I can take it away and I can replace it with one that intersects it minimally. Okay, that's something I can do. And now I get a new Pants decomposition. This one's different. Okay. So what I've just done there is called an elementary move. So if I have P and Q belonging to this set here, they span an edge if they differ by an elementary move. Okay, so what are the elementary moves that I'm allowing? If somewhere on the surface this topologically, this is a topological drawing, so any of these can be marked points or whatever, I can move from this curve here to this curve here. Another curve that intersects it minimally, that's one possibility. Or if I'm topologically have a subsurface that looks like this, I can move from this one to this one. Okay, so I'd like to immediately notice that this is an everywhere infinite degree graph, no matter what your surface is, because I chose this green surface here, but I can take this back, this red curve here. Okay, and there's a natural homeomorphism of the surface that's obtained by den twisting along this. Okay, so I can twist, 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 twist like crazy. And I can get another curve that has exactly the same properties, which of course I will not be able to draw, but I'll draw anyway. So something like this. Okay, so here's an example of another curve. No, okay, I went the wrong way. Going here, and then I'm going back around. No, hold on, where do I want to go? Going boom. I went this way, so then I come back. And then I want to go right. So that's this. Good grief. Why am I not doing this right? Okay, well, something I can compare. Here's one. Okay, there we go. It's not exactly the curve I was hoping for, but doesn't matter. Here's another curve that I could have chosen. Okay, and I can twist along this many times, hit the curve, go around many times. Okay, and I'm going to get another class. So in fact, what's happening here is I'm moving around locally in the fairy graph that I was describing before. Okay, in this Pants graph here, what I'm getting, just by fixing all of these red curves, except for this one, and I'm moving around just in this, what I get is a copy of the fairy graph. So you immediately see that this Pants graph contains these copies of these fairy graphs. Okay. Ah, yeah, because maybe I didn't say this, but these are all the same curve graphs. Okay, the fairy graph of the curve graph for these three examples is always the same. It's always the fairy graph, which I didn't prove to you, but you have to take faith. Okay. So let me see. Something that's maybe not obvious to people is that this new graph is also connected. And the reason it's not as obvious as in the case of the curve graph is that there's no sort of elementary surgery argument that's going to help me lower the intersection between two pairs of pants, between two pants decompositions. Okay, I mean, that's not a very convincing argument to say that I can't do the argument that I did before, but I can't do the argument that I did before. Okay, it doesn't work, at least not as simply as you might hope. In fact, there's no explicit, I mean, it's not difficult to prove that there is one, but there's no sort of explicit formula that gives you distance in the pants graph only in terms of intersection number between two pairs of pants. Okay, so it's not so easy to see this. But what I'm going to do is I'm going to prove it on the complexity of, I'm going to prove it by induction on the complexity of this. And this will be a nice occasion to introduce the complexity. So, okay, so given the topological surface, the complexity kappa of this topological surface is equal to 3g minus 3 plus n is the number of curves in a pants decomposition. Okay. Interior curves in a pants decomposition. Okay, so how am I going to prove this? So I have now P, and I want to get to some Q, and they both lie in a pants decomposition. I want to find a path. Okay, how do I find a path that goes from P to Q in the pants? So by induction, well, I want to start off with, if K is equal to 1, then I'm in one of the three cases I talked about before. Okay, this is the curve graph, the pants graph. So this is the set of surfaces that have one curve as an element of the pants decomposition. Well, it means I have a one-hole sphere, one-hole torus, or a four-hole sphere.
Maybe three-hole sphere.
And the three-hole sphere is empty.
Where it's empty?
Well, because there's no curves. There's nothing. There's no.
The isotopy doesn't permit you to go through the puncture.
I mean, what happens is right, exactly. So a three-punctured sphere doesn't have any essential simple closed curves.
Just go around one puncture.
Yes, but that goes through the puncture. So what I want is, so if I have a three-hole sphere, okay, and I try to find a simple closed curve that's disjoint from the three punctures,
Yes.
okay, then I have to do something like this, okay, which is automatically parallel to this, which by my definition is non-essential. There's all sorts of interesting structures on closed curves of the three-punctured sphere, okay, but not on simple closed curves. Okay, or if you change your definition and you take that, then essentially you're going to get a finite number of curves. But, I mean, I'm just supposing that we're not in this case. Okay, so from our point of view, this one is empty. And in any case, there's no, yeah, so, okay. So in this case here, then sigma is equal to the four-punctured sphere, or the one-punctured torus. Okay, it doesn't even make sense to talk about pants decompositions of a torus. Okay, so I'm really in one of these cases. Okay, in both of this case, then this is really the curve graph. In both of these cases, and it's connected. Okay, so I want to get from P to Q, and now by induction, what can I suppose if I take gamma that's a curve belonging just a curve belonging to Q. So if I can find a P prime, which also contains Q, which also contains gamma, which is reachable by a path leaving Then by induction, I'm done. Okay, so why is that? So I find some path that gets to some pants decomposition that contains a curve that belongs to Q. Okay, I take this curve, I open along it, and I look at the surface that I have underneath. Okay, so why is that true? So I have gamma somewhere on the surface. Okay, this is sigma. I cut along sigma to get this surface here. Okay, this is sigma cut along gamma. The complexity of this surface is now -1. Okay, so now I can only make flips on the Pants graph of this surface. These clearly correspond to some move on the Pants graph of this surface, and I can get from any Pants decomposition on this one to any other ones by induction. Okay, so now I move in Pants graph of this one. Okay, I clearly have a copy of this one inside the Pants graph of this one. Okay. So now I want to find any Pants decomposition that contains a given curve of Q from this original Pants decomposition. So what do I do? So P is going to be equal to some collection. P is equal to alpha 1 union alpha, the complexity of gamma. Okay, it's the union of a bunch of curves. And I take alpha 1, I choose it, alpha 1 like this, and what I do is I construct a path that lies in the curve complex this time, between alpha 1 and gamma. So this is a path in the curve complex of gamma. So I know there's some path between alpha 1 and gamma that lies in the curve complex. Okay, so how am I going to use this to say anything about a path that lies in the Pants complex? So what do I know? Well, if I denote this curve here, so I'm going to give these curves names. This is going to be gamma 1. This one's going to be gamma 0. I'm just going to rename it. This is gamma 2, so forth. And this one here is going to be gamma k. Okay, so what do I know? I know that gamma 1 and alpha 1 are disjoint. Okay, so I'm going to take a multi-curve. Okay, so a collection of curves that belong to the curve complex. Okay, so this is a multi-curve. I should, yeah. It's not the graph. Okay, so how should I mean, this really does belong to the curve complex, a multi-curve. Okay, just a union of disjoint curves, such that alpha 1, gamma 1, and mu 1 form a Pants decomposition. So alpha 1 and mu 1 are disjoint, so I have two curves, and I complete this into some Pants decomposition. Okay, and this is going to be called, I'm going to call this, by definition, P1. So, if I think about this, I have P1 here. So now I have a path P1, and I look at my original P. Okay, so P1 and P, they both belong to the Pants graph. Okay. By definition, they have a curve in common. They have alpha 1 in common. Okay, does everybody sort of agree with that? So P has alpha 1, and P1 has alpha 1. So they have a curve in common. So by induction, there's a path that goes from P to P1. maybe it makes many stops, but there is a path that goes from P to P1. Okay. Because they have alpha 1 in common. The same argument that I used above.
What's nothing a little confusing. So alpha 1 union gamma 1 two curves. Mu 1 is another.
It's a multi-curve. So this one has
Oh, I see.
the complexity of gamma minus 2 curves.
Oh, okay. So
I'm just completing these two curves into a Pants decomposition. Okay. So I have another Pants decomposition, and it has a curve in common with P. So by induction, I said that if the surface had less complexity, okay, one less complexity, I can find a path between two Pants decompositions. So what I'm doing is I'm cutting along alpha 1, doing the same thing I did before, and just moving around to the Pants graph of this subsurface, okay, to get from one Pants decomposition to another Pants decomposition. Okay, so this, by induction, I can do. Now this P1, what am I going to do? I'm going to do the same thing over and over again. How am I going to construct P2? Okay, so P2, I'm going to make sure it contains gamma 2 and gamma 1. Okay, so P2, I'm going to do the same way, and I'm going to do this for every Pk. Okay, it's going to be gamma k minus 1, union gamma k, union mu k, okay, where they form a Pants decomposition. And now my induction hypothesis is going to allow me again to go from P1 to P2, because now P2 contains gamma 1, and this one also contains gamma 1. So they have one curve in common, so I can move along here. Okay, and then I can just sort of keep on going. Until I eventually get to Pk, which by definition, which in this case I'm going to take as P prime. Which is a curve that by definition contains gamma. Does that make sense? So to get from P1 to P2, P2 to P3, I just keep on moving on these complexity -1 subsurfaces. And then eventually I get to this last curve, which by construction contains gamma, which is what I wanted to show. I wanted to show that I can get to a Pants decomposition that contained this curve gamma. Okay, and then again, this means that I'm done. Okay, sort of the underlying idea behind this is a sort of a very simple version of what's called hierarchy in the curve complex.
Excuse me. So here, so once you choose a path in the complex curves,
Yeah.
you can construct such a chain. So is there any bound on the length of step you need once you have a bound on the path in the curve complex?
Well, no.
No.
No, because, I mean, not the way I've done it.
Huh?
First of all, because I've chosen my Pants decompositions by
That-
chance.
Yeah.
Okay.
You don't know
So,
which way.
I mean, you could do this in a more intelligent way to try to get bends.
Uh-huh.
Yeah. I mean, you could ask, for instance, that these paths be geodesic in each of the underlying Pants complexes, and you can ask for all sorts of things. And you can try to choose the Pants decompositions intelligently, but this is not at all what I've done.
Okay. Yeah, yeah. Here, I mean, you just choose random.
Exactly. Exactly. All right. So boy, how far have I gotten? Not very far. Okay, so maybe I should just essentially stop here. But before I stop, I'm just going to say what I'm going to do in the next lecture, which is later on today, so you won't have time to forget. is that I want to talk about Weil-Petersen distance. And I'm just going to give you the definition, and then in the next lecture I'll talk about properties of it. And the definition is going to be meaningless to those who don't know what it is, and completely useless to those who do know what it is. Okay, so this is a meaningless moment where everybody can close their eyes. Okay, and I'm going to say words like, okay, so the cotangent space of in a point x that belongs to the Teichmüller space, okay, is associated with so-called quadratic, holomorphic quadratic differentials. Whatever. Okay, so if you don't know why this is true, then there's nothing I can do that can help you. Okay, but locally these are just things of the form h of x, h of z times dz squared. Okay. Okay, so because of this, if you look at rho of x, which is the line element corresponding to the Riemannian metric on x, okay, you get a natural metric as follows. So if you take phi and other phi that belong to this one here, okay, this is an area element. Okay, so you integrate it. And what you do is you get this L2 structure, you get a product by looking at the integral over x of this. And if you take the real part, you get the Weil-Petersen metric, or in this case it's the co-metric, because you've defined it over, you've defined it on the cotangent space. Okay, this actually gives you a Riemannian metric on Teichmüller space. Okay, and I will use absolutely none of that in what follows. Okay, so I'm going to stop here. Thank you.
Questions to the speaker?
Yeah.
Is there a way to going from a path between 2 points in your complex of spans to another path, as for example in the complex of triangulation, of IV triangulation? And can you define some kind of simply connectivity?
Can you define some kind of what, sorry?
Can you define some canonical way to go from a path to another one for you complex to be simply connected?
No, I mean I don't. No.
Okay.
No. I mean there's of course you can do everything by analogy, but
Yeah, but
yeah.
there is no.
No, there's no. I mean as far as I know, there's no canonical way of doing it.
What do you want to prove? You want to prove come that?
No, but for example, if you take the complex of triangulation, so it's connected, and if you take 2 paths from a triangulation to another one, there is some way to go from a path to another, another one.
Okay, so
with
you
some
want
relation, for example, of flip, of tetragrammaton, and this kind of thing.
Yeah. I mean yeah, there's no. It's
So
no.
there is nothing like that.
I mean there's no canonical way that I know.
Yeah, okay.
What boundary on infinity describes this complex of Pan's decompositions?
So what's
Earth
the,
complex describes some, in general, the boundary of Teichmüller space.
right?
So
But what do you want? So
in Weil-Petersen metric.
so in the Weil-Petersen metric, I'm going to talk about what the boundary is.
Okay.
But yeah, but so the Pantz graph is not Gromov hyperbolic. So in particular, you don't have a Gromov boundary.
Okay.
So it's more, it's another.
No, probably it describes some parts of boundary in Weil-Petersen metric of Teichmüller space. Or not.
Not really. I mean, it's more you have sort of it's the sort of the appropriate notion is looking at visual spheres and things like that. And yeah.
So how much information is lost if you go from curve complex to curve graph?
Well, let's see. Maybe Athanase knows the answer to this question.
Yeah, homotopy type, which is informed in the coordinate.
No, but the question is like whether or not you can recuperate the complex from the curve.
Some triangles, for instance.
Yeah, right. Yeah, you want to know whether you can recuperate it from the. Yeah, I mean, in the case of there's examples where you don't lose anything.
Yeah.
Yeah, I don't know the exact for the curve complex. I don't actually know. It seems like you might actually lose things. For the pants graph or the arc complex, for instance, you don't lose anything.
Yeah.
I have a question. Since you mentioned the Wade-Peterson metric,
Yeah.
why did Wade introduce this metric?
Why did he introduce this metric?
Yeah.
To bug me. No, it was he introduced it in a letter to Peterson, right?
Yes.
And and I don't remember exactly what his argument was, but
so he did not have any application for that, I guess.
I don't think he had any application in mind. I think he's just sort of said it's natural.
Okay, like that. Okay.
I don't know that. I've never actually seen the letter. But
Okay.
it's just from the point of view of hyperbolic geometry, regardless of a technical definition or not. What's interesting here is that it's an L2 metric. And what I didn't say is that this is very close to it. So this is sort of an L2 metric, and you can do the same thing for an L1 metric. And here what you're integrating is actually just sort of, well, let's put it this way. If you look at the norm, okay, you can do the same thing here. You get a norm from this. And the norm you get for the L1 metric, this is the Teichmüller conorm. And the point to this is that a Teichmüller metric is any local deformation of your surface is going to create a lot of distance. Whereas in the Wade-Peterson metric, you're always averaging over the whole entire hyperbolic metric on the surface. Just as an L2, you'd expect an L2 metric to behave. And that's one of the sort of the key properties of this metric.
More questions? Well, let's take this picture down. And the last speaker for this morning is Louis Trunard. He will speak about quantum invariance of three manifolds.